amount of time in electronics removing the charge from our calculation. The construct of the electric field was the first. In talking about you can't see that. Full diversion. So we can go back to work, right? Wait. Bow. We can go back to work now? All right. All right, all jokes aside, let's get back to work. That was a nice, successful diversion. If I have a charged particle here, that's positive charge, and it's in a region of space where there's a uniform electric field, it is clearly going to be experiencing an upward force due to that field. We know that because, by definition, we have defined the electric field based on the way a particle behaves in the region of space. Again, we define the field by removing the value of the charge so we could say something about the space. Saying that suggests that moving the particle from here to here must increase its potential energy. Can you guys kind of get on board with that? In the same way that lifting the object in a gravitational field would increase its potential energy, moving the particle against the field should increase its potential energy. In fact, what we would like to do is establish the concept of the electric field and the concept of the electric potential as being something that is about the nature of the space that the particle resides in, but also define it based on the same tenets that we used in mechanics to deal with energy. What we would like is a construct of energy that is universal in all applications of physics. We talked last year about what is energy, and what we came to the grips with by the end of our conversation on that day was anything that would do work, we would say, is energy. Something that could change something's kinetic energy would also be energy, but that's kind of a circular definition. So we say the capacity to do work is energy. Well, we want to have the same kind of definition no matter what form of energy we discuss: chemical energy, thermal energy, and in this case, electrical energy. So the simple, non-calculus way to talk about this is to say that, well, the work done on the particle would still have to be force times change in position. If I use a uniform electric field, as I am in this circumstance, then I can write this as Q times E times the change in position. But again, if we're going from this location to this location, the work that's been done is against the field. And that dot product would produce a -1. With that in mind, we want to define potential energy. So this is electrical potential energy as minus the work done by the field, or positive QE delta X. Now this is for a uniform field. So I'm being really careful because I'm trying to compare it to the same thing we had in our discussion about mechanics, where the amount of potential energy was mg delta H. So we have the same things here, except that instead of G, our expression for the electric field is capital E. The lowercase g really was an expression of the gravitational field. Q represents the same kind of quantity that M represents. It's an intrinsic property, and it is a force-carrying property, meaning the charge experiences a force because it has charge. Again, it's a difficult thing to define, but we kind of tried to talk about that. Now, we want to take away the charge from this conversation, which is why yesterday I kind of talked about it, but today I would like to define the electric potential, and I want to do that by writing it as a change in potential from one place to another as minus the work done divided by the charge. I would like my changes in potential to be similar to changes in potential energy, in that an increase in potential suggests a region of space where there will be an increase in potential energy. Everybody understand what I just said? Because I want to be very careful about it. And I want you to have the vocabulary. I want consistency between mechanics and electronics. And I want, therefore, an increase in potential to be equivalent to an increase in potential energy. So I want to make sure I have consistency here. So taking a positive charge and moving it against a field increases that charge's potential energy. I therefore like the change in position to yield a change in electric potential that is also positive, suggesting that there's something about the space here that is different than the space here. That a particle that is placed in this location would have more electric potential energy than a particle placed in this location. Is that a reasonable argument? Here's where that argument begins to have a little bit of trouble when we talk about electronics. What if my particle has a negative charge? Which direction is an increase in electric potential for the particle? I'm sorry, I should have said that different. Which way is an increase in electric potential energy for the particle? Up. So if I take this particle and shift it upwards, I am increasing its electric potential energy. But if I shift it downwards, I am decreasing its electric potential energy. Therefore, we are going to define positive electric potentials as places where positive particles have an increase in potential energy. Right, we have to be more specific. There was no negative mass before when we had mechanics. But in electronics, because we can have positive and negative charges increase their energy when they go against the field. Negative charges increase their potential energy when they go with the field. This seems easy now, but please note that that's probably going to be something that is easily confused, especially since we will discover later that the actual particles moving in all circuits are negative. So everything that we talk about in here is based on the movement of positive particles, but we'll find in electronics it's negative particles that are actually doing the moving. So again, it's an increase in potential to go against the field. Increase in potential. We define positivity of the field based on what a positive charge does. Uniform field, I mean, if it's uniform, then it's the same everywhere. There would be no place where there's zero potential energy. So consider a region of space that has an electric field like this. What would generate an electric field like that? Yeah, a sphere of charge or a point charge would generate an electric field like this. So it is likely that, although nothing's pictured here, it's likely there's some concentration of positive charge. Agreed? I don't need to know what's there. I just need to have a knowledge of what the electric field is. So we'll say this electric field is from a concentration of positive charge. We know that's going to look something like that, right? That's the shape of that electric field. It has spherical symmetry, dies off as 1 over the distance squared. If I label 2 points on the field, A and B, where's the higher potential? So it's reasonably clear that to go against the field, A, being closer, is going to be at a higher potential than B. Agreed? Now, the difference here is our field isn't uniform. You recognize that if I actually want to take a particle of positive charge and try and move it, well, that's not going to work, is it? Let's move it just a little bit over there. There we go. If I want to take this particle and move it from B to A, I'm not going to be moving it against a constant force, but a constantly increasing force. So let's introduce some stops in the middle. 1, 2, and 3. Do you think the change in potential from B to 1 is going to be the same as the change in potential from 3 to A? Very unlikely, right? Because we have a change in force, so how much our potential changes is going to have to be different. Now, there's another issue here, and one that I need to make sure we understand, and that is our gravitational fields were largely constant for almost all of the year until we discussed gravity, and only in mechanics, end of the year, did we discuss the fact that gravity had a unique property once you got away from being near the surface of the Earth. And we talked about the gravitational field being just like this electric field. Dropping off is 1 over the distance squared. Do you remember how we had to find a way to define gravitational potential energy differently because of that? Do you guys remember that conversation at all? That we had to consider the idea that in space, how do we know what zero potential is? Or zero potential energy is? In this region of space, is there a place where a particle has zero potential energy? I mean, we had the in this case, is there a place that's got zero potential energy? Well, in the theoretical, if we can get far enough away from the particle where it's no longer reasonably interacting with the field, then we might be at a place where we can assume the particle has zero potential energy. This is inspiring the difference between what we say when we say electric potential and electric potential difference. Capital V by itself is considered electric potential. It is derived from considering a change in potential where the initial potential was zero. While most of the time, what we will have in space are just changes in potential. But because this is a theoretical class, we will have to consider the possibility or the idea that we could discuss situations where we have an absolute potential. This represents an absolute relative This would have to be relative to a place in space where the particle would have no potential energy. These two words are considered different. However, and I don't mean to throw this on you all at once, but these words tend to get thrown around interchangeably. You have to keep up with whether we're dealing with something that has a true electric potential, which means we're measuring it relative to a zero, or whether we're dealing with an electric potential difference. Problems are not always clear on this. And worse, they are often all lumped in under one title, voltage, since the unit of the electric potential is the volt. Now, in order to put all of these pieces together, we're going to define the electric potential difference as the change in potential energy divided by the unit charge, which is going to be minus the work done divided by the charge. Which, if we do all the substitutions that we talked about today and deal with the directional issues we talked about today, that will bring a definition of the change in electric potential as minus E dot dr from an initial location to a final location. And the electric potential, similarly defined, but looking for a place where this is zero. This only works for fields that do decay. So we would never be able to find the absolute electric potential in a uniform field because it doesn't decay. It doesn't go away. Now, if you think of the three basic shapes, two of them have the opportunity for us to measure this as an absolute. The line of infinite charge for sure, and the point charge for sure. They both decay over distance. So if you get far enough away from them, we can assume we're far enough away where the electric field in that region of space is zero. Now, I'd like to take a look at an example of how you would have to use this. Consider the point charge as we started this discussion. So having a point charge in space, Q. We know the electric field around this point charge is of the shape Q over 4 pi epsilon naught r squared. If I want to move the charge from one location to another, or compare two places in space, one location to another, I could find a way to calculate that change in potential. Now, we're going to do the math on this, but I want to also impress upon you knowing what the change in potential gives us. If we know the change in potential, then for any charge, we probably can figure out the potential energy, or at least the change in potential energy, as that would be Q times delta V. If we know the change in potential energy, it is possible we will know the change in kinetic energy. Meaning if I drop the charge at one place, I could probably figure out how much change in potential energy I have at the other place. That might sound like no big deal, but when we had it for gravity, our force was constant. So we could use things like Galileo's laws of motion to figure out how fast something changed. That's why we did gravity questions in the first 2 weeks of the school year, because we could. You couldn't do that here. Right? We couldn't use a motion equation to describe the force on a charged particle. If I say I'm going to drop a charge right here and ask how fast is it going when it makes it here, well, that would be a challenging thing to do because the force is changing the whole time. But if I can calculate the change in potential between the two places, then I can tell you how fast it's going because that has to equate to a change in potential energy. Or consider the opposite of that. Oftentimes, collider experiments fire a particle towards another particle. Knowing where that particle stops tells you how much energy the particle must have started with. Because you can figure out what the change in potential energy is by where it stopped, because that's got to be where the electric potential was. The potential that stopped it. In fact, you'll hear phrases like starting and stopping potentials. What potential is being used to start a particle into motion, and what potential is being used to stop a particle from motion. These aren't esoteric ideas. A long time ago, and by long I mean probably before you guys remember, there were TVs like the one in the back of the room. You guys see it? The big box sitting in the corner? It's there. All the way in the back, a huge, massive box. It's got a screen about this big. In the back of that box is an electron gun. The electron gun itself is probably only about a square centimeter in surface area and probably about a couple of millimeters wide. It's really small. And to make a electron gun, all you need is an exposed light bulb and a region of space that has 2 plates to generate a uniform electric field. We know that a sheet of charge generates a uniform electric field. If I can put 2 sheets of charge in space, one positive and one negative, I can contain between them a uniform electric field. A light bulb glows because it gets hot, and when it gets hot, electrons will boil off the surface. They'll just come right off because they're hot enough to break away from the metal. Electrons are negative. They will experience an accelerating potential that will drive them across the plates. This is called a starting potential. It starts the particles into motion, gives them kinetic energy. By setting the electric potential between the plates, you can determine how fast the particles travel. So this is called a starting potential. This is how you would use it. Now, those TVs worked by having an electron shot from the back of the television and hit a glass screen that had trapped gas in it. So when the electron was steered towards that piece of trapped gas, the amount of energy the electron had excited the gas and made the gas glow a specific color or a specific brightness. Depends on how the TV was designed to operate. So you would fire the electrons towards the front of the screen, and that would cause that particular area to glow. And that's how we did TVs for nearly 60 years until we started getting flat panel and active panel displays. But this is how sorry to bore you. This is how you did it. Again, the idea was that we can use the concept of a potential to accelerate a particle to a given velocity. And we can manipulate that potential to change how fast they're going. The best part is, I don't really need to know very much about the space. Like, I don't have to know how big this is. If you recognize what we did, delta V equals delta U over the charge. And delta U equals change in kinetic energy. Nowhere in there do I have to know, well, how far apart are the plates? What is the electric field? I don't have to know any of that. I just drop a particle here. It instantly has energy because of the region of space it's in. I didn't have to pull the particles back and then release them like some kind of slingshot. I didn't have to lift something up against gravity and then drop it. Because we can manipulate charges so freely, all I had to do is find a way to drop the charges into that region of space. So it takes a lot less energy to just boil off these electrons, but then because of where they are, they instantaneously have an incredible amount of energy. By the way,